All right, let's go ahead and work some practice problems now. So let's assume that we have a compound that contains the following grams or masses of carbon, hydrogen, and oxygen, and that we know the molar mass of the compound is 138 grams. So we want to determine the empirical formula and then from that the molecular formula. The first thing we need to do is change the grams of each element into moles, because chemical formulas are not written in grams, but they're written in moles. So for the carbon, we'll multiply by the conversion 1 mole for 12 grams to give us 0.137 moles. We'll do the same thing with hydrogen using 1 gram per mole, and oxygen using 16 grams per mole. So these are the number of moles of each substance in our formula, but we still don't have the chemical formula because those are not whole numbers. A chemical formula has to have whole numbers. It can't be C.137, H.411, and O.0685. So we have to find a way to change those decimal values into whole numbers. And there's a very simple little method of doing that. It's not really a chemistry thing, it's simply a mathematical tool. What you do is you divide each of the mole values by whichever the smallest one is of your group. And that was, of course, the moles of oxygen. If we go back and take a look, of the 3 mole values we had, the oxygen was the smallest. So we want to divide all 3 of these by the moles of oxygen. So dividing the moles of carbon by the moles of oxygen comes out to be 2. Moles of hydrogen divided by moles of oxygen is 6. And of course the moles of oxygen divided by itself comes out to be 1. So now we have nice whole numbers, and now we can come up with a good empirical formula, which would be C2H6O. So this is the simplest ratio. It doesn't actually tell us what the formula is, but it tells us what the ratio of the elements are. The way we figure that out, of course, the actual formula is we need to look at the molar mass. So if we look down here, if we add up 2 C's, 6 H's, and 1 O, we find out that our empirical formula has a mass of 46 grams. If we divide that into 138 grams, which was the molar mass of the actual compound, the molar mass of the compound divided by the mass of the empirical formula should always be a whole number. If it's not, then you have a problem. And so this tells us that the molecular formula of the compound is actually 3 times greater than the empirical formula. So the molecular formula would be C6H18O3. Okay, in this next problem, we're going to make one small change. Instead of the grams of each element, I've given you the percentages of each element, which is pretty common. So how do we deal with percentages? Because when we do the calculations, of course, we need grams. The first step is normally to change grams into moles. So how do we figure out a number of grams? And it's actually pretty straightforward. If we know how much of the compound we have, we simply multiply the grams of however much we've started with by each of these percentages. If we started with 13 grams of the compound, we'd figure out what 27.27% of 13 grams is, and that would be our mass. And we do the same thing for the hydrogen and the nitrogen and the oxygen. Of course, we don't know how much of the compound we're starting with, and luckily that doesn't matter, because we can start with any amount we want. For example, if you have a teaspoon of sugar, the formula is C12H22O11. If you have a 5-pound bag of sugar, is the formula different? Of course not. It's still C12H22O11. If you have a truckload of sugar, it's the same. So the composition of a compound doesn't depend on how much you have. So we can simply pick whatever we think is the easiest amount of compound to start with, and that turns out to be 100 grams. So to get the masses to do this first step, we're going to assume that we have 100 grams of the compound, since we can assume any amount. And of course, 27.27% of 100 grams is 27.27. Very simple. Same is true with the hydrogen, the nitrogen, and oxygen. Whatever the three percentages are, the grams is the same. So the take-home lesson for problems you do in the future is you don't need to do this calculation. If you assume there's 100 grams of the sample, and you're free to assume any amount you want, then the percentages and the grams will be exactly the same. So if you see a percentage in a problem, just change it to grams and use the same number. So now that we have our grams, we can move on to the next step and do what we did last time, which is convert the grams to moles. So we'll take those four percentages, which we've now called grams, and we'll use the molar mass of each of the four elements, just like we did before, and convert the grams into moles. Now, one thing I didn't mention in the previous problem, and might be confusing some of you, I've been hounding you about the idea that certain elements come in pairs. It's always H2 and N2 and O2. And that's true as long as the element is by itself. So the element hydrogen by itself is H2. The element nitrogen by itself is N2, and oxygen by itself is O2. But when elements are part of a chemical compound, that rule no longer applies. For example, water, H2O, only has one oxygen. So that's why we're dividing by the mass of only one atom rather than two, just so you remember that for future reference. So now that we've got the moles of each of the substances, now we can figure out the mole ratio. Like we did before, we're going to divide by the smallest number of moles. Well, it turns out in this case it's a three-way tie. Carbon, nitrogen, and oxygen all were equally small. Hydrogen was the larger. So we can pick any one of these three as our denominator. So we'll just use oxygen since we did that last time. So we can divide the moles of carbon by the moles of oxygen, like we did before, comes out to be 1. We divide the moles of hydrogen by oxygen, we get 2. Moles of nitrogen over the moles of oxygen is 1. And of course, the moles of oxygen divided by the moles of oxygen would also be 1. So we get 1, 2, 1, and 1. And that means our empirical formula will be CH2NO. Like we did last time, we need to figure out what the mass is of CH2NO. So if we add up a mole of carbon, 2 moles of hydrogen, 1 of nitrogen, and 1 of oxygen, we get a molar mass of 44 grams per mole. If we divide the actual molar mass by the mass of the empirical formula, we get a nice whole number. In this case, it's 4, and therefore the molecular formula will be 4 times greater, or C4H8N4O4. All right, let's do one more problem, and I'm going to throw another twist into this one, which you'll see in a moment. So we've still got our percentages, so we're going to do what we did last time. I'm going to use percentages, but what we learned, of course, from the previous problem is whatever these percentages are in the question, we can simply use those as grams. So we can assume there's 42.1 grams of carbon, 8.77 grams of hydrogen, and 49.1 grams of nitrogen. So our first step, as always, is to change the number of grams of each element into moles. And so we do the same thing we've done in the previous examples. We use the molar mass of each element to convert the grams into moles, and we'll come up with these 3 values for moles. Our second step, of course, is to come up with a mole ratio by dividing by the smallest value in the mole column, which happens to be the nitrogen, the 3.507. So we'll divide all the mole values by the moles of nitrogen. So moles of carbon divided by moles of nitrogen is 1. Moles of hydrogen divided by nitrogen is 2.5. And the moles of nitrogen by itself, of course, is 1. So the new wrinkle that I've thrown in here is this did not come out to be a whole number. The hydrogen came out to be a fraction, 2.5. Well, if we think back to when we were balancing equations, sometimes when we balanced combustion reactions, we would end up with something like 6.5 O2. And how did we fix that problem? Well, we simply multiplied everything by 2. If we had a half in a balanced equation, we simply doubled everybody to make them whole numbers, just like we would do in a math problem. So we can do the same thing here. We can simply double each of these, because just like in algebra, as long as you do the same thing to everybody, it's fine. So now we simply made the carbon is 2, hydrogen is 5, and the nitrogen is 2. We still have that same ratio, but now they're nice whole numbers. So that gives us an empirical formula of C2H5N2. We then want to figure out the molar mass of the empirical formula, which is 57 grams. We then divide the molar mass of the compound by the mass of the empirical formula. We get a multiplier of 2, and therefore the molecular formula will be C4H10N4.